You're on.
Welcome back to Bayesian Statistics, you guys. Today I'm going to finish up the lecture of Jefferys prior, and then Dr. Lima is going to get started on the Wishart distribution discussion. With that in mind, for homework 3 again, there are 2 problems, a subpart of problem 4 and problem 6 that deal with the Wishart distribution. Those problems you can hold off until next homework. If you want to give them a shot, go ahead. It's always good to get a head start. Second, there's going to be an in-class midterm on Wednesday. In-class midterm. So be here Wednesday to take that. With all the logistics done, let's get back to Jefferys prior. So let's get a reminder of where we were last time, what we reviewed, and then what we're going to do today. So last class, we said we had some data that came from a normal, and we had 2 experimenters, one operating underneath mu, and another experimenter operating under a different parameterization, which was 1 over phi, or psi, 1 over psi. And our goal is to infer mu. So we have our 2 experimenters, and they have their likelihoods. Question, do we need a Jacobian when we just do this quick plug-in? We're just plugging 1 over psi into our mu is for the likelihood. Do we need a Jacobian? No. Good. All right. Also, another question. Who knows? Does anyone know what this distribution is? Any guesses? Any guesses?
It's normal, but it's not exactly normal.
So Martin said it's a normal, but it's not exactly normal. So it's a normal with mean 1 over psi. Some of us might be tempted to call this an inverse normal. And we don't want to do that because inverse normal already has a distribution and it's different. An inverse normal deals with Brownian motion and that type of stuff. So maybe we can call this a reciprocal normal, but it really doesn't have a name. So just want to get you guys knowing some distributions and if there are names to them. We went on and we said if these experimenters worked under non-invariant to what should always be a question, to transforms in our case. And in our case, we also use the uniform prior on our parameters. So under this rule, everything's going to have a uniform prior. What I mean by that is our prior on mu for experimenter 1 is the flat prior, or uniform, and our prior for psi is 1 also. Okay? We ended up seeing that these 2 experimenters with the same data will get different answers. My question to you is, how did these 2 answers differ? Thank you, Jess. Always got my back. How did those 2, if we need to, let me bring up my notes from last time. So we had experimenter 1 that came up with mu, and this was their distribution. And then we had experimenter 2, who after using their psi did a transformation, and we had the transform on mu. And these 2 distributions differ by this term right here. How did we get that term?
Multiplied by the Jacobian.
Yes, good job, Stephen. Thank you. That is all because of the Jacobian in our transforms. Okay? So they differ by Jacobian. And it's not good to have our answers differ when we're trying to do estimation and inference on the same parameter. So under the non-invariant transform, experimenter 1 and experimenter 2 aren't using the same prior. Although our priors are 1, 1, when we actually do the math, they're not working at the same thing. So we decided, let's try and use an invariant to transforms prior, which was the Jefferys, and we saw that if we use mu, Fisher's information, to the 1/2, we will get 1. And then if we do the same thing for psi, we'll get 1 over psi squared. On Monday, our lecture had some issues, so I had to go re-record it. At the end of the new lecture, which I re-recorded and posted, I worked out the Jeffrey prior from you. So that is online. I want you guys to go back through it. A good practice, some of you guys have been asking how can we practice for the midterm? A good practice, prove this to yourself. Okay? It's just how we get more practice. Now remember, for Fisher's information, I'm going to use theta just so we can be general, is the expectation with respect to x, taking the derivative, log. Last time I said likelihood, you can do likelihood, sampling, distribution, won't matter. Square. Okay? This can also equal if there's a certain condition, expectation of x, there's a minus sign, second derivative, log. This only holds, these are only equal if what condition holds? Oh, thanks, Jess, keep reminding. This only holds if what condition? Yes, Muhammad. Convenience. So while these two priors look different, they contain the same information. Our experimenter's priors contain the same information. Now, what we're going to do, that was all a recap from last class. What we're going to do this class is we are going to show you guys why Jeffrey's prior is inherently transform invariant. Okay? So let's get started. So question to ourselves. Everyone good with this page? Cool. Just making sure. So our question is we kind of want to prove it to ourselves. And before we get straight to the proof, I'm going to recall a couple of things we've learned in class. The first thing is, let's remind ourselves of transforms. We've been doing a lot of these lately, but let's just give ourselves a transform of density functions. So we have a density function on phi, and we want to theta. So we have a relationship such that theta is equal to G inverse psi. And we're going to transform our distribution from theta to psi. Sometimes we've been writing this as theta, or pi theta times theta over psi. Okay? Now, I'm going to give you a fact, and we're going to come back in a moment and prove this fact. So, fact. Fisher's info for psi will be equal to Fisher's info of theta times absolute with respect to theta. Oh, that's supposed to be wrong. Squared. We're going to come back and prove this. So for the next 30 seconds, believe me, I'll prove it. Now, if we look from this fact, which is using Fisher's information, and we look at the transform rule, we're very similar. And all we have to do is take the square root on both sides to have it match. So let's take the square root. So Jefferys wanted to invoke the transform of the information in this analysis, and it turns out the square root of the Fisher's information provides us with transform invariant. And so this is why we have Jefferys prior pi, just using the J and these two classes to denote this, theta is going to be proportional to Fisher's information. Boom. And so in last class, when we were doing all the derivations to figure out what our Jeffery prior was for mu and v and psi, we were doing Fisher's information 1/2. Now I got to prove to you guys that this fact holds. Okay? Any questions thus far? Okay? So we're going to start on this side in our proof. So we have Fisher's information of phi, and we're just going to follow our definition real quick. It's the expectation with respect to x d theta, or psi phi. Oh, let me repeat that. Derivative with respect to psi. So many different letters today. Log x conditioned on psi squared. Okay? Now, we're going to want to transform this so that we can use theta. Okay? So, transform into theta. Where again, our phi is equal to some function of theta, or it can be written as theta is some function inverse of phi. Just remember that relationship. So we have the expectation respect to x. And now we're going to apply the chain rule. We're going to have d theta. I'm going to write it all out and then I'll talk about it. I want to write that black. Okay? We're applying the chain rule here. The non-mathematical way to see this pretty quickly going from back here to here is these two d theta cancel out. It's not the most mathematical approach, but you're using chain rule to get from here to here. I want to note that this black F distribution and this red one are not the same. Notice that this has phi and this has theta. I'm just using F to represent, hey, it's a density. So it's also why I try to change the color on you guys, so you know they're not the same, and it's just representing the density. Sound good? Okay. Now, we're just going to take this square and bring it through. I'm going to keep this red so we know it's not the same. Squared. Squared. Boom. Now, we're taking the expectation with respect to x. This does not have x in it, so it can be pulled out. And we're going to be left with d theta log b squared. Now, who can tell me what this is?
Information matrix for,
Louder?
that is information matrix for X, no, for Z.
Good. Martin said it's the information, Fisher's information for theta, which can be represented as I theta, d theta, d phi squared. And thus, the fact that I told you to believe here is shown. And then we're just taking the square root. So this is proving to us that the Jefferys is inherently transform invariant. There's an assumption we're making though. And this assumption is that our model assumptions are the same. So if we automatically don't have the same model assumption, so we're both not using a normal, then this isn't going to hold. So we have to have the same model assumption for this to follow. Any questions? Okay. Now I'm going to give you guys a little note, some things to think about. As we show with the,
Can you actually explain what Fubini's is?
So Fubini's is the property where we can switch our intervals in and out. And so when it doesn't hold is when our parameters are on the bounds and that. Does that help a little bit? It's giving us the ability to switch our derivatives in our intervals. And that's going to help us. If you want, we can talk more about that after class. Sound good? Cool. Any other questions? That was a great question. Okay. Where was I on? Our two experiments at the beginning, we had them use a non-invariant prior. Everyone used to use a uniform. Here's the caveat. As we get more data, and we assume we don't put zero mass in our prior, so we don't just have zero in our prior, we will eventually, asymptotically, as we get more data, converge to the same thing. It's all about that likelihood getting more peaky as we get more data. Okay? So that's one thing that's cool is, yes, our priors don't match, but if we get a lot of data, the prior won't have as much impact. The one thing that also Jefferys gives us is that it is a reference prior in 1D. And Bernardo and Smith ended up doing the proof of this. In higher D, this is not true. The next question is, what's a reference prior? Reference prior is just that says that our prior does not have, it has minimal impact on your posterior distribution. Okay? just a couple of words you guys will hear throughout the time in tech. So the question, some of you guys might be thinking, is as we go higher deep, how do we get our Jefferys priors? And sometimes, when we've done it in this class, where we end up using the marginal of the Jefferys. So in our joint posterior for psi and mu, we use the Jeffery prior 1 over psi and 1, correct? That might be a little bit. Let me just write that out so we see what's... So when we were looking at the likelihood of mu and sigma squared, conditional on data, which is proportional to 1 over square root. We'll keep it simple. To create the posterior for mu and sigma squared, x, we use the prior mu flat and sigma squared 1 over sigma squared. These are the marginal Jefferys for mu and sigma, and we're using those to help our posterior. Okay? And so some people don't like that, but computationally that's a little bit easier. And then when we start going to Gibbs, we know our full conditions. Are there any questions? I know I threw a couple words at you. Yes, no.
So you said that when we're using Jefferys, the parameterization does not matter asymptotically.
So the question was, when we use Jefferys prior, the prior does not matter asymptotically?
Parameterization.
The parameterization. That's a good question. So I was talking more about priors in general. So if we were using the flat for both, and we have a lot of data, those two priors aren't going to have as much impact. Does that make sense? Okay. Good question.
So I'm a little bit confused as to what Jefferys is. You said that whenever your data gets really large, you always converge to the true distribution. So what's different about Jefferys?
Okay, can you name a problem for me where we have infinite amount of data?
Off my head, but I'm like thinking, so what does Jefferys give us? So because what we said is that asymptotically, you get the same answers.
Correct.
Using Jefferys.
So asymptotic, you don't need to use just Jefferys. You could, this is in general, we have two priors. We could have priors that are really wrong, but as we get more data, it's all about that likelihood. So our posterior is going to be likelihood times prior. And so we have a likelihood, let's say that's our likelihood right now. And I could have a prior. Let's say I'm going to make my prior this. Completely wrong, being very subjective, throwing it way out there. But if I was to get more and more data, our likelihood, we're going to pretend that's all centered at the same spot, is going to get peakier and peakier. And so our likelihood is going to take over as we get more and more and more data, it's going to take over. The one thing you don't want to do, and where this asymptotically fails, is if here's my prior, here's a new prior. Let me give a new 10. We'll go green. New prior. We're going to put a bunch of weight and then 0. More weight. We're putting 0 where our thing is. This is never going to help us. We're pretty much saying you can never get there on your prior. That's not going to help. Does that help a little bit answer your question?
So the Jefferys gives you with the same inference. You don't have to asymptotic.
Yes. So It's more small sample sizes. So in small sample size, Bayes is going to really help us regularize, make sure we're in the same spot. Jefferys is making sure we're not getting changed by that Jacobian factor, and that in small sample sizes, hey, we're going to match. As we go higher and get more and more data, then a lot of Bayesians and frequentists are going to start matching. We have a bunch of data that we can use to help us. Does that help? Awesome. Any other questions? Then I think this is a great time to segue to learn about Wishart distributions with Dr. Lehman.
All right.
Here for a compelling lecture. I'll just add to Mohammed's question. Sierra was saying a lot at the end, but basically, we want priors so that we get good inferences in our posterior. If we're going to come up with a default prior, we want it so that regardless of what arbitrary parameterization you're using, the answers are the same, in the sense that if I transform the distribution, I get the same distribution as everybody else that's using a Jefferys prior. What Sierra was saying at the very end was the formulation she gave you is height measurement. So instead of just having that absolute value sign, you'll have that Jacobian matrix, and you'll take the determinant of it, and then you'll take the absolute value of that. Sometimes I don't really see people use joint Jefferys priors very often. I've done it in some papers. So I do it in cases like I'm going to be able to compute everything on this particular scale, but at the end of the day, I'm going to transform it. And so I need to think about what I'm going to do. So I've done that in logistic regression. So if I ended up trying to take the betas in a logistic regression, take some function of them that's meaningful to me, I want to make sure I didn't do anything too weird with the prior. Now I'll do a couple of things. I'll do maybe the joint Jefferys. I'll also do the marginal Jefferys and see how the answer is different. And so I usually will report that. Most people do kind of the marginal Jefferys thing. Sometimes you'll see people do the joint reference analysis, and that is different than joint Jefferys. So lots of priors that we still need to learn about. I think what Sierra was saying is, she's telling you how she applies it in practice. In a lot of analyses that she works on, people are only interested in the margins of the distribution. Thinking about the joint relationship is maybe too complex for us. And so she at least makes sure her margins are transform invariant. And that's good. She also said that if you did something different but reasonable and you had a lot of data, our answers would converge into each other. So experimenter 1 and experimenter 2, if they use Jefferys priors, they get the same answers. Might not look the same because of the transform that you're working in, but if you transform one distribution, it'll match the other experimenter's distribution. If you use the non-invariant rule, flat prior everywhere, which is a terrible idea on things like scale parameters, those boundary effects can really get you. If you were using flat priors there, and I say it's terrible, but you were data rich, your prior's not going to have much weight in the analysis. And so even if you did mess up, and most statisticians don't just write down Jefferys prior and go to town on it, we do have differences in our analyses. Sometimes people like to impose subjective information through the priors. They might have good reason for it. But at least asymptotically, as we get a lot of data, our prior assumptions aren't going to overwhelm us. The likelihood is going to speak very loudly. So lots to chew on there. That was kind of a long lecture on basically just a property about Fisher's information. That the half power of Fisher information transforms just like a probability distribution does. And that's the whole thing. That's like once you write down that one step, I thought what Sierra did was highly mathematical. She said maybe it wasn't the most mathematical explanation. That Jacobian term is just the chain rule. And so if you go back to calculus, it's there. Okay, I want to switch gears. Talk about Wishart distributions, and I want to motivate this through a problem. This is the problem that I think the world got introduced to with Gibbs sampling. So we're going to try to connect a lot of our knowledge. Second. So if you go to the webpage, on the schedule, I cut up a couple links for you. There's two different links right there. One has to do with the precision matrix and how you interpret the elements of a precision matrix. It's just a two-page write-up that I did for you. Instead of giving you a whole lecture on precision matrices, i.e. the inverse of the covariance matrix, I just dropped it into a document. So read through that. If you've ever taken a regression class, basically the elements are akin to the, what do you call it? Since I can't think of the name, it's in the paper. So the partial correlations, if you're familiar with those. There's also another link that takes us to one of Gelfand and Smith's very early papers. So while there's a paper that we talk about all the time, Gelfand and Smith, 1990, JASA, there's about 4 other papers that led up to that paper. And all these 4 papers are essentially the same. And so this is about how I operate as a statistician, that I get an applied problem, I work on it, and later on I'll develop general theory. So I'll show how to apply it, and then I do the theory. How does this all generalize? A lot of people in the math stratosphere flip that around. You know, they do all the theory and then they're searching for a problem. I think that the trends are changing these days. This paper was written in 1989. And so it's got a lot of authors on it. The 2 interior authors are scientists. And so Adrian Smith was working over in England. Gelfand was working at the University of Connecticut. He did his sabbatical with Adrian Smith. And then Ellen came back and worked with these guys over at Stanford. They had a problem. And I'm going to tell you what the problem was in just a moment. But I kind of think it's fun to read through this paper. It's different than what papers look like now. And so this is like the type setting. It's pretty old-fashioned, it looks like. Formulas are a little bit hard to read in here. But if you squint hard enough and you look at this long enough, you'll be able to match some of the notation to what we do. They have inverse gamma distributions floating around in here. So that's their IG. So they're doing everything on a variance scale. So you'll have everything on maybe a gamma scale for this problem you're doing. So which prior are you going to use if you're going to work on a different parameterization? So that's a good question. Sierra provided you a lot of thought for that. Their priors are subjective, and they tell you what the inputs are into this. You'll have to read through the paper. And then they present you with some data. Check this out. I love this. Formula, tables. There's their data set. So 1989, scientists worked very hard to collect this data right here. So what this is it's rat weights varying over time. And so they have 5 different rats, and they have 10 different measurements, or they have 30 different measurements for each rat. So 5 rats, 30 measurements, and those measurements are taken every week. So this is a 30-week study. I love this. So nowadays you can't put your data in papers. So we're gonna make a text file of this and give it to you for the next homework set. I'll probably just type that myself, so only one person has to do it. And we're gonna have you code out there, give sampling. So, and see how your results compare. Now, they might not be exact if you pick different priors, but they should be semi-close. I'm not sure exactly what they did in this study, but basically, they had two different groups of rats. This is kind of the idea. They do something to a rat, and they want to see how it affects them. So a typical measurement is their weight. So we're just going to stick with that. There's something that they're doing to the rat, and they want to see how it affects their weight. Okay. If you don't like thinking about rats, something like that, you might think about when you go to the gym, what's your goal? You know, are you trying to cut on weight? You trying to take off weight? There's different things that you'll do in the gym. And so you track the results week after week after week, and you have some sort of intervention. I'm overloading on protein powder. So lots of protein powder, I'm trying to get swole. So let's see if it's working. You know, you jump on the scale. Maybe you're going the other way. You want to slenderize a little bit. So you're doing a lot of treadmill time. You've got this new fancy vitamin. They promised to give you results. So you check your weight over time. Okay, so in the context of human beings, we can think about a similar problem. We will have this data set, and you can just see if you can match their results in this paper. But let me tell you what their model was. So I'm going to tell you about this paper, because it's a little bit hard to read. It's old. There's about 4 of them, but it did this over and over and over and over again. A couple different data sets, a couple different explanations, how much modeling, how much science, how much math. And so they go back and forth in these different papers until we get to their Gibbs sampling paper in JASA. Okay, so I'm going to write down a pretty simplified time series model. We're going to think of this as though we're doing work in 1989. A lot of you are going to say, why don't we just change that whole model altogether? I have a better model for you. And I've got better models too. So, but this is 1989, and things were different then. So we're going to be sympathetic, and we're going to accept their model. I think you'll agree once I show it to you, it's pretty basic. Okay. So I'm going to change my notation a little bit. To just let the X's in their paper, I think they had XIJ. And I'm just going to keep reminding you, this is the weight for rat I in week T. Okay, so I'm going to change the notation just so that we understand whatever this context is. If you don't like doing experiments on rats, I understand, change that to person. You can go experiment on people and think about ourselves in the weight room or something like that. Okay. Here's their model. So they're going to take, they want to model these right here, the weights. Oops. So I want to model these things. T is going to go from 1 to cap T. In the paper, that was 30 weeks. And J, or I, is going to go from 1 to cap. Usually we'll make that like an N or something like that. If I don't give you the indices and say what they are in the context of the problem, you're able to just choose them. Okay. Usually that would be N. Let's stick with N. I don't know why we do this. That's the number of rats. So this, they were pretty clever with, and they ended up making this normal 0 sigma squared. So very ambitious model. Let's think about what this model says. So in a typical sort of time series setting, I might do an auto regression. I might regress the weights on each other. They didn't do that. They made this very simple. That basically, they're just looking for linear increases in weight over time. They did do one clever thing right here, is they said, let these coefficients be rat specific. So I. So they put indices on this. So alpha I, beta I are rat parameters. These are the parameters that Gelfand and Smith think control rat weights. And each rat is a little bit different. So if I didn't put the eyes on there, what we could do is try to see how weight changed over time for the whole population. But I've got multiple measurements for the same rat. So my conjecture is that different rats have different weight parameters. Go home.
Aren't we essentially using 5 different models this way?
Kind of, yeah, but this ties it together. So I wouldn't say they're completely separate. So they're all tied together through the same variance. So this is called random effect. So alpha and I, beta I, the rat parameters, those are random effects. Bayesians and non-Bayesians both use random effect models. Basically, they do the exact same thing. So regardless of how you think about it, it's pretty contentious when you bring this up with a bunch of frequentists and Bayesians in the same room, because they can't figure out what's a prior and what's a random effect distribution. Here's my secret to you. Who cares? If you like that model, call it whatever you want. So last step to this, I'm going to call this theta I, right here. I'm going to say theta I is distributed in some fashion. So we're going to be real clever. This is what Gelfand and Smith did, is they said theta i's are going to be tied together through some population parameters. So I'm going to say this is theta naught, and this is sigma, right here. If you'd like some other notation, we could call that alpha naught, beta naught. And this right here is a 4 by 4, or a 2 by 2. So it's just looking at the correlation between those parameters. So if you were a Bayesian, you'd say, oh, that looks like a prior distribution. And you would have some interpretation for it, that these are the parameters in the underlying population, and this is how they relate to each other. Now, you could call that a prior if you wanted, but that's not how we come up with priors. That's part of the model, and that's saying something to us. So if you were a non-Bayesian, you would estimate these parameters, the alpha i's, beta i's, through something that looked just like a posterior. You'd call it a random effect distribution. How would you handle all the other parameters in the model? That, and that. Right there, you would maybe do maximum likelihood. So they'll mix these two different techniques. If you're a Bayesian, I'm going to put a prior distribution on all those. And everything looks like a posterior update. So that's kind of the idea. So we want to learn this parameter, this parameter, this parameter, and all of those parameters. So for all of the rats. Let's give this a little bit of interpretation. I think this is kind of one of the questions that they were trying to answer in this paper, and this was hard to do once upon a time, is fit this model. Computers were pretty lightweight in '89. Anybody even born in '89? So if you remember?
My dad had a computer from that time.
Commodore PET, an Apple IIe, Apple IIc.
No, it wasn't an Apple, it was an IBM PC.
Okay, yeah.
US.
So I remember those days. I grew up in Silicon Valley, so I had a Commodore. Not too sophisticated. So one of the bigger questions here is, are these elements right here non-zero? Do these two parameters relate to each other? And that's what they're trying to answer. If they didn't build that in, it's a pretty easy problem for most people, even way back when. But they're trying to understand the relationship between these two parameters. So what does this actually mean? That they're correlated. Let's think about it a little bit. So do you think this should be correlated with that? In the context of our story, we need to give those parameters some interpretation. So the beta I, that's how you put on weight through time. So how the rat puts on weight. If it's very positive, they're putting on weight fast. So whatever they've done to it, sped up maybe its weight gain. If it's negative, they drop weight. So that's how it's interpreted. This parameter right here is kind of your baseline weight. So at time 0, that's the weight of the rat. That's how I interpret it. So weight at time 0. So that's kind of a baseline thing. So I like to give all my parameters interpretations and know what they mean so I can tell the story. It's not just a math problem. What do you think? Do you think that these should be related with each other? So Mohammed says yes. So Mohammed's saying, hey, if you show up to the gym, back to our gym example, and you're big, you're gonna put on weight fast. So we've all seen it, you know. Skinny people show up to the gym and they're trying to put on weight and they can't do it as well as the person that was already big. It can also go the other way, too. If the person's very big, they might have a lot of weight to lose as well. And so does your initial weight have something to do with your propensity for putting on weight? I think the answer is probably. Now, I've heard people say, I don't think so. So you might have a different opinion and you can argue it the other way, and that's good. So what do you do to answer the question? You go and collect data and you measure these things.
So suppose you go to T like -10 or something, like just when the rat was born, and then all it weighs is starts at 0 and the next year is just like T. So what does that do?
There's stochasticity. I've got sigma squared in there and some normal there. So no, it's not deterministic.
I mean in terms of the relationship between alpha and beta. So that when
Yeah, so
alpha is like the first beta.
maybe, but maybe it changes every week a little bit. Maybe there's some flutter. Maybe I misread the measurements and there's flutter for that reason. So I don't really care what the reason is for inducing the stochasticity. I'd still say it's random. Now, you might be right scientifically, I don't know. But I'd still expect, under data that comes from an experiment, to see something that looks not deterministic. So, and there's any number of reasons that can happen. But I don't know, so I'm not sure. So the idea in all of this is we want to be able to estimate all of these parameters right here. That parameter, that right here, and the big question is about this correlation between everything. We also have to measure this parameter as well. And so we've got a whole bunch of stuff we need to measure. The next lecture I'm going to give you is about how you actually do inference on a matrix. So it turns out standard distribution for doing inferences on matrices is to use an Wishart distribution. And it turns out in this case it's going to be inverse Wishart, but on sigma inverse we're going to use a Wishart distribution. So that problem in the homework pertains to this example right here, and I've asked you in that homework to write down the full conditionals for all of the problem, all of the parameters. Hold off on the full conditional for that one, if you will. If you want to do it, go ahead. It's just a conjugate analysis. So Wishart is the conjugate prior in this case. We know what the conjugate priors are for all the other parameters. So what Gelfand and Smith did is they didn't just like estimate that model by maximizing it or something like that. They ran it through a Gibbs sampler. And that was their motivation for developing the Gibbs sampler paper that everybody celebrates now. This is the problem that they were first introduced to. So pretty simple problem, but back in 1989, this is revolutionary. So what they're going to do is they're going to write down the full conditionals for these, that, and that. And they're going to iteratively update those full conditionals. And it will converge to the joint posterior on all of those parameters. This was considered high dimensional once upon a time. And so nowadays, things are even higher dimensional. So we'll come back to this, study Wishart distributions, recap what this problem is. But why don't you think about it a little bit? What do you think the relationship is between those two parameters? And let's have a 1-minute discussion on it, and then we'll get into under the hood and back and forth. Thanks, you guys. Appreciate it. While you guys are getting ready, I'll just have you stare at that thing. That's the Wishart distribution. So the distribution of our matrix. That's a matrix, that's a scalar. And I'll point out to you just real quickly. In 1D, this looks like a gamma distribution. So see if you can convince yourself of all of that. I'm trying to remind yourself what traces are. I think the most recent homework has done that for you. But the motivation for that trace stuff is in this